present our next speaker, which is Mikhail Muzychuk, and he will speak about some criterion solvability of finite groups. And please, you are welcome.
Thank you, William. First, I'd like to thank the organizers for invitation. Now, my talk, as you can see, is not really about algebraic graph theory. It will be about linear representations of finite groups. But I have one slide where I pose a problem about association schemes. So in this sense, the topic of my talk fits the scope of the workshop. Now, this is a joint work with Zalman Balanov and his PhD student Haopin Wu. Here they are. So they are from University of Texas in Dallas. So for Zalman Balanov, I have to say that I worked with him for quite a long time period in Israel at the same educational institution. And actually, he was my next door colleague. So, and at a certain time point, he started asking me questions about representation theory of finite groups. And we started to think about that. And the result of this thinking was published, after all, in the paper you see in the bottom of the slide. It was published in the Journal of Algebra. So if you compare the title of my talk with the title of the paper, you can realize that actually there are not much in common. The intersection between words of two titles is almost empty. And this is because only recently I learned the notion of Sylow branching coefficients from the talk of Eugenia Gianelli. And I realized that they are related to what we had done with Zalman in this paper. And I will show you the definition of these things and how they are related to the topic of my talk. Now, the motivation for Zalman. So if you look at the title of the paper, you will see that it is about Brouwer degree, and not just an arbitrary Brouwer degree, but a Brouwer degree of what is called equivariant map. And this is because Zalman motivation came from differential equations. So he considered a differential equation like that. So x prime is p of x plus some small supplement h. This one. For the sake of simplicity, we may think that h is 0. So you can think that you have a differential equation like x prime is equal to p of x, where p is a nice function. So in this case, we assume that it's polynomial, but in general, it could be any continuous map. And the main question that was interesting for Zalman was which conditions on P do ensure an existence of periodic solution. So if P is a linear map, then the answer is well known. So for example, if you take the linear map corresponding to the following matrix, right, then the differential equation has periodic solutions, which are the usual cosine and sine. But in nonlinear case, the question is much more difficult. So, and there are certain conditions when you can prove that the solutions you need, they do exist. So, and these conditions are related, what is called a Brouwer degree of a map. So I'm not going to determine or define what is a Brouwer degree, but it's known that for every continuous map which maps a compact manifold to Euclidean space, you can associate an integer number. So, and if this integer number, which is called Brouwer degree of the map, is non-zero, then, and some other condition is satisfied, the third one, then you can say that there are solutions. There are solutions for your equations which are periodic. Now, the problem with this approach is that in general, Brouwer degree is not easy to calculate. So if P is linear, then it is easy. You just take the determinant. If it's positive, then the Brouwer degree is 1. If it's negative, it's -1. But if it's a nonlinear map, then it's more difficult. And it turns out that you can prove sometimes that a Brouwer degree is non-zero without computing it. So, and this happens when your function P that you have here, it is equivariant with respect to some group action. So let me recall what is an equivariant. What is an equivariant function? So you have two linear representation of a finite group, finite dimensional. So that means you have some rho which maps G to the set to the automorphism group of V, and you have some sigma which maps G to the automorphism group of W. So these homomorphisms, they define the action of the group on these vector spaces, and the function is called equivariant if it commutes with the action of G. So to be more formal, I have to write here. I have to write here rho of G, and here I have to write sigma of G, right? But in general, that means that G commutes, that phi commutes with the action of G. Now, a simple example of equivariant map is this one. So you take a representation of Z2 on the one-dimensional real space, which maps X to -X. Then any odd function will be equivariant with respect to this action. A more complicated, but still not a difficult one, is a following example. You take a plane, consider it as a field of complex numbers, and consider the following map, which maps Z to the 5. Then you can check that this is an equivariant map with respect to the group Z4, just if you multiply any, if you multiply Z by the element from the cyclic group of 44 generated by I, then you see that this is an equivariant action. And there are some other examples of equivariant action, of equivariant functions. Now, how this is related to Brouwer degree, and these two things are related via so-called congruence principle. The theorem which was proved by Balanov and Kushkuley, and it says the following: assume you have two linear representation of a finite group G. Both of them are orthogonal or unitary. Now take the, so if it is a orthogonal or unitary, it fixes the unit sphere setwise. So you may consider the action of your group on the unit sphere, and because your group is finite, all orbits will be finite too. And then you can define the greatest common divisor of the cardinalities of these orbits. And this parameter, the greatest common divisor, is denoted alpha of the sphere, or it is called alpha characteristic of the representation. So assume that there is an equivariant map from V to W for which we do know how to calculate Brouwer degree. Then for any equivariant map for which Brouwer degree is correctly defined, we have this congruence. Okay. So if your function phi is good enough, for example, if it is linear, then its degree is either 1 or -1, then you have very nice congruence, which ensures that Brouwer degree of psi is non-zero. But this you can say only if the alpha characteristic is greater than 1, right? And so now the question is focused on two things. You have a representation of the group. Now you take the orbits of G action, and you take the greatest common divisor of the lengths. So you get this parameter, which is called alpha characteristic. And we want this parameter to be greater than 1. And in order to be able to compare the degrees, we need some equivariant map with which we can compare, which can participate, which we can plug in this congruence here, right? So here, now we have two problems. So in order to apply efficiently congruence principle, we need two things, as I already told. This, we need to find this phi, and we need to we need alpha to be bigger than 1. Now there is one case when we can easily find the map which has non-zero Brouwer degree. It's a identity map. If V and W is the same vector space, or we have the same linear representation of G, so you can take phi to be the identity map, and then we have this congruence. And now what we need is to know when this number alpha of V is bigger than 1. So here I wrote alpha of V, but before that it was alpha of SV. So the orbits on a unit sphere, but there is no difference because any orbit, if you have an orthogonal representation, and if you take any orbit, it consists of the vectors of the same length, so it can be mapped by multiplied by a certain scalar to a unit sphere. So there is no difference between considering the alpha characteristic of the sphere of the whole space, but the only thing we have to do is to remove zero vector. So from now on, I'm talking about this alpha of V as the greatest common divisor of orbits among non-zero vectors. So now, in order to apply the congruence principle, we are faced with two problems. Problems A, when the alpha characteristic is greater than 1, and problem B that I'm not going to talk about it later, but it is the second problem in this approach. Find a good equivariant map for which we can find its Brouwer degree. So starting from now, we can forget everything we heard about Brouwer degree, differential equations, etc. Starting from now, what we are dealing is we have a linear representation of finite group G of dimension D over field F. And in my talk, the field F will be field of complex numbers, but it also could be any field of characteristic 0, and some of results could be generalized for the cases when the characteristic of F is positive. Okay? So now you take your representation, take the orbits on non-zero vectors and take their greatest common divisor. Now, because the orbit length always divides the order of the group, the greatest common divisor always divides the group order. So we always have this thing. Now, an extremal case is when alpha characteristic is equal to the group order. In this case, the group G acts semi-regularly on all non-zero vectors. Or another name for that is fixed point free action. So in this case, if alpha rho is equal to the order of the group, we get a fixed point free subgroup of a general linear group. And in the case when the field is complex, is the field of complex numbers, all such fixed point free subgroups, or all free subgroups were classified, and you can find this classification in the monograph of Wolf, which is from 1936. Now, but this is somehow an extreme case. It doesn't occur often. So we are interested in what happens when the group is not a fixed point free subgroup. What can we say about alpha characteristics then? Now, first, how we compute the alpha characteristic? Well, you take the action on non-zero vectors. For every vector, you get its point stabilizer, right? It's a subgroup, and the length of the orbits is the index of that subgroup. So the conjugacy class of that subgroup is called an orbit type of the vector. And now we denote by phi GV the set of all orbit types, right? So these are set of conjugacy classes of subgroups. So some subgroups could appear there and some of them not. And now the alpha characteristic is just you have to take the greatest common divisors divisor of the indices of that subgroup. Or you can say it differently. You can say, take the least common multiple of all orbit type subgroups, orders, and then divide the group order by that number. So the first bad news is that we cannot compute the alpha characteristic from the character table. And this is because there are groups which have the same character table, but have different alpha characteristic. For example, if you take the dihedral group and the quaternion group, they have the same character table. Both of them have unique two-dimensional irreducible representation. Now, the quaternion group in this representation acts fixed point freely. So the alpha characteristic for quaternion group in two-dimensional representation is 8. But if you take the dihedral group of order 8, then its two-dimensional representation actually is real, and it acts on a plane, and its alpha characteristic is 4. So they're different. It's not enough to know the character table in order to compute the alpha characteristic. Now, here are some examples. So let us take the symmetric group on 4 lattice, which acts in a natural way on 4 points, and every permutation representation produces a linear permutation representation, right? But if I take the original action, it is not irreducible. There is a vector which is fixed by all elements of G. This is all one vector, right? So if I compute the alpha characteristic of the whole permutation model, it will be 1. So it's not interesting. Let us take an irreducible subspace which consists of those vectors which sum up to 0. And let us make a look on the vectors which and their stabilizers. So if I take a vector with all distinct coordinates like 1, 2, 3, -6, then the only permutation which stabilizes it is identity. So if I take a vector with 2 equal coordinates, for example, like that one, then its stabilizer is cyclic group of order 2. Now, if I have 3 coordinates equal, then it will be the symmetric group of order 3. And if I have a vector of that type, say 1, 1, -1, -1, then the stabilizer will be Z2 cross Z2. So now if I take the greatest, the least common multiple of the orders, so 1, 2, 6, and 4, I will get 12. So 24 divided by 12 is 2. So this is an alpha characteristic of three-dimensional irreducible representation. Now you can compute the alpha characteristic of all irreducible representation of S4. Of course, a trivial representation has a trivial alpha characteristic. This another one-dimensional representation is sine, right? So it has the alpha characteristic too, because this is one-dimensional and every orbit consists of 2 elements, x and -x. Now, if we take a 2-dimensional representation, it comes from the fact that the symmetric group S3 is the quotient of S4, and S3 has 2-dimensional irreducible representation, and this is it. And its alpha characteristic is 3. Now, the fourth one is the one we computed the alpha characteristic, and you can take the tensor product of a sign representation with this one, and its alpha characteristic is 4. Right? So this is a case of the symmetric group of degree 4. Now, what happens if I take the smallest simple group, A5? So the group A5 has 5 representations. One is trivial, 2 3-dimensionals. These are group representation which corresponds to the symmetric group of the polytopes, icosahedron. Now it has an irreducible representation of dimension 4, which comes from 2 transitive action on 5 points. And it has an irreducible representation of degree 5, which comes from 2-dimensional 2 transitive action on 6 points. Now here, what is written, these are the stabilizers of the vectors. And now you can take the least common multiple of this stabilizer, take its index, and you will see what is the alpha characteristic. Now you see the only space where alpha characteristic is 1 is this 5-dimensional one. Okay. And the others are non-trivial. So we have 2 examples of groups. One group has alpha characteristic non-trivial for any non-trivial representation, and the other has one representation with a trivial alpha characteristic. So this leads us to 2 questions. What can we say about group if all its non-trivial, irreducible complex representation have non-trivial alpha characteristic? And actually, this question was of main interest for my co-author, Zalman Balanov. And the second one actually appeared when we started to begin the subject. So what can you say about the group if all irreducible representations have trivial alpha characteristic, right? Now some properties of alpha characteristic. So if I have a direct sum of 2 G modules, then its alpha characteristic is GCD of alpha characteristic of its summons. So actually, if you want to know the alpha characteristic of any G module, you have to compute it only for irreducibles. Okay. Now, here we have that alpha characteristic of tensor product divides the product of alpha characteristics. So here the division could be proper. So there are examples when the alpha characteristic of tensor product is equal to the product, and there are examples when it is not equal. So the one where it is not equal, if you take the group S3 and take the unique irreducible 2-dimensional representation, its alpha characteristic is 3. But if you take its tensor product with itself, then you will find that there is a trivial representation in the decomposition of this tensor product. So the alpha characteristic is 1. So the division is proper. Now, if you have 2 models which are Galois conjugate, they have the same alpha characteristic, and this is because they have the same set of vector stabilizers. Phi GU, okay. Then if one module is obtained from another one by applying the automorphism, then the vector stabilizers are obtained from the vector stabilizers also by applying the same automorphism, so the indices will be the same, and so the alpha characteristic will be the same too. Now, what about induction and restriction? So, whenever you have an irreducible representation, you can restrict it to a subgroup, and you can induct it, and you can induce a representation of a subgroup to a representation of the whole group. Now we have this one. Oops, sorry. We have this connection. So the alpha characteristic of the restricted representation always divides the alpha characteristic of the module. Why is that? Because any orbit of G is union of orbits of its subgroup. So if some number divides the length of every H suborbit of every H orbit, it certainly divides the length of any G orbit. So now this condition also is a division condition. Now, but it holds when H is normal. If H is not normal, then it's not necessarily that this condition holds. For example, if you take the S3 as a G and S2 as an H, take a unique non-trivial module of S2, then induce it, and then you will get the induced model is a decomposition of a sign representation and two-dimensional representation. Sign representation has characteristic 2, two-dimensional has alpha characteristic 3, so the greatest common divisor of them is 1, right? But alpha of u in this case is equal to 2. So this divisibility condition holds only if H is normal subgroup. Now, from this, we can get very useful corollary, which says if P is a prime divisor of a group order, and I want to know what is the highest P power, so this element here, is the highest P power which divides the alpha characteristic. So what I have to do, I have to restrict my representation to a Sylow P subgroup and compute the alpha characteristic of that. Now, from this, you can actually understand whether the alpha characteristic is divisible by P or not. Because the alpha characteristic is divisible by P if this one is divisible by B. And this is divisible by P if and only if you don't obtain a trivial representation in the decomposition. If this representation, I mean the restriction has only non-trivial constituents, then all orbits there will be divisible by P. So therefore, if you want to know, if you don't want to know what is the exact number of your alpha characteristic, but whether it's divisible by P or not, you have to look at this at the alpha characteristic on the restriction. If there is trivial representation, then the alpha characteristic is 0, is co-prime to P. Otherwise, it is divisible by P. And because the multiplicity of trivial representation of P in the restricted representation is the same as the multiplicity of V in the reduced representation by Frobenius reciprocity, then actually what you have to do in order to understand which irreducible representation have co-prime alpha characteristic, you have to look at those which appears in the reduced representation of your Sylow P subgroup. And this is how we get to Sylow branching coefficients. Now, this I learned, as I told you, from Eugenia Janelli. So take a Sylow P subgroup and consider the action of your group G on the cosets of P, let's say left cosets. Then what you get is a permutation representation, but it's also a linear representation. And its character is what is called the induced character. It's the induced character here. And now you take any irreducible character of your group G and you count how many times it appears in the decomposition of the induced one, and you get this number. And this is called Sylow branching coefficient of chi. So the induced character is decomposed in this way, and omega 1 of P denotes the set of all characters which have non-zero coefficients. That means those which really appear in the decomposition. And now I want to cite the theorem, which was proved by Mallet and Navarra. So they said, they proved that if you take a finite group and P is Sylow subgroup, then P is normal in G if and only if every character that appears in the decomposition of the induced one has a degree coprime to P. And now I want to formulate the question related to association schemes. Now, what happens in this theorem is this. Let us look at the action of group G on the cosets, its transitive action. We know that every transitive action has an association scheme which is associated to it, right? Which was called a V ring by Wieland. So, and the relations of this association scheme are two orbits of G. They are in one-to-one correspondence with a double coset of P. Now, and if you look at this association scheme, then what properties it has? So all valences are powers of the same prime P, right? Now, all multiplicities of irreducible characters of the scheme. Now, remember that multiplicities of irreducible characters of the schemes are the dimensions of irreducible characters of the group which appear. So all multiplicities are coprime to P, and the number of points is prime to P. Now, the question, is it true that in this condition, the scheme should be thin? Now, if I take a Schurian association scheme, then using theorem of Mallet and Navarra, I can say, yes, it is true. But what about non-Schurian, right? What about if your scheme is even commutative? Can you prove that? So this is a relationship to association scheme, but I'm going further to tell you about more details of alpha characteristic. Okay. So, and this here is a proposition which gives you some equivalent condition for what I already told before, when a prime P divides the alpha characteristic, right? So let rho be a reducible representation of G, chi its character, take a prime P, take a Sylow subgroup, and now the following conditions are equivalent. So P divides the alpha characteristic. Trivial representation is not a constituent of the restriction. Yeah. So the rho is not a constituent of the induced representation. So which is the same as saying that chi is not in the set omega. And this condition is important for us in the future. What is P underline? P underline, here I used notation from Wieland's book. So P underline is the sum of all elements in P, and it belongs to the group ring. So it's an element of a group ring. Now, if you take this proposition and apply it to all primes, you get this corollary that a reducible representation has trivial alpha characteristic if and only if it is contained in the intersection of all this induced representation. Or in other words, its alpha characteristic is one if and only if it appears in every induced representation from every Sylow subgroup. Okay, that's now I'm coming to solvability criterion, how it is related to alpha characteristic. And given a finite group G, the following conditions are equivalent. G is solvable. Alpha characteristic of any non-trivial irreducible representation is non-trivial. And the intersection of all these omegas, this intersection should contain only trivial representation. Now we know that this second and the third are equivalent. Now I'm going to prove that the first and the second are equivalent. And this is the solvability criterion that I was talking about. So let us show, so I'm showing now that the group is solvable if and only if alpha characteristic of any irreducible non-trivial representation is non-trivial. Now, one direction, I'm assuming G is G is solvable. And as I told you, I assume that the field is field of complex numbers, but you can see from some proofs that it's not needed. Now, let's take any reducible representation. So here I'm not assuming that G is solvable, right? So take the kernel of this representation. Take the maximal normal P subgroup of this kernel and assume it's not equal to 1, then I claim that P divides the alpha characteristic. So why is that? So first of all, you can factor out your group by the kernel. You get G bar. So now you have a faithful representation of G bar. Now take the subspace consisting of all vectors fixed by OPG bar, okay? So this is a subspace and it's G bar invariant. Because it's G bar invariant and we have an irreducible representation, there are two options. Either this is the whole space, either it's 0. But it cannot be the whole space because of this condition, okay? OPX non-trivial is there. So it is 0. That means OP of G bar, this normal subgroup, does not fix any vector besides 0. But that means that every orbit has length, which is a power of P, non-trivial power of P. And so, I mean, the orbit of OPG is has length divisible by P. But if this is true, then this is true for any orbit of G. So one direction, so the proposition is proved. And now, then we have a corollary that for any irreducible representation of solvable group, I mean non-trivial one, the alpha characteristic is non-zero. In fact, you can say more than that. You can say that the alpha characteristic is divisible by any prime divisor of the fitting subgroup of this quotient. So this is a solvable group, take its fitting subgroup. Every prime divisor of fitting subgroup divides the alpha characteristic there. Okay, so now we prove it in the one direction. The proof in the other direction is more complicated. It's very non-trivial. It doesn't use the classification of finite simple groups, but it's based on the other work that I'm going to cite later. So in order to prove the other direction, let's define what is a complete system of Sylow subgroups. So you take all primes that you have. For example, for A5, you have 3 primes, 2, 3, 5. So fix any order of them. And for every prime, pick an arbitrary Sylow P subgroup. And this is called a complete system of Sylow subgroups. Another thing we need is a proposition which says an element in a group algebra belongs to the principal ideal generated by this element. So we know what it is. This is one-dimensional ideal spanned by this element. So X is in this ideal if and only if any non-trivial representation vanishes on this element. So I'm not going to prove that because it's more or less clear, and I'm going to the proof of the following proposition. Assume we have a finite group G, fixed ordering of the prime divisors P1 up to Pk. And the following are equivalent. For any non-trivial irreducible representation, there is a Sylow P subgroup such that this is 0, and we know that means that P divides alpha characteristic of rho, okay? So for any irreducible representation, there exists a Sylow P subgroup such that rho vanishes on this formal sum. And the second condition, the product of all Sylow of any complete system of Sylow subgroups is equal to G. Okay, these two things are equivalent. Now, well, let me show one direction. Let me show one direction. So I take the product of these elements in group algebra, right? So let's call it by pi. Now I want to show it's equal to G underline, right? And if I show that, then it follows from me that the product of all Sylow subgroups is equal to G. So now picking arbitrary irreducible representation, it vanishes on sum of PIs. So if I take rho of this product, right, on some PIs it's 0, so rho of pi is 0 for this representation. And this is an arbitrary non-trivial representation. So from here it follows that, and from the proposition I told before, that pi is proportional to the G underline, but now I apply to both sides the trivial representation, or one could say I use the counting arguments. Then I get that lambda is 1. Okay. Now, since time is running, just want to show you the other direction. So the proof is on the slides. If you want, you can read it from the slides. Now the proof on the other direction also works. Now the solvability criterion. So one consequence of the proposition is a whole theorem, which says if G is solvable, then the product of any complete system of Sylow subgroups is equal to G, right? And this is follows from the results I presented. The other direction was proved by Kaplan and Levy in 2005. They proved that if product of any complete system of Sylow subgroups is equal to G, then G is solvable. So now we have if and only if. So this proves the theorem I presented you. Now, the result of Kaplan and Levy is based on the famous Thomson paper about local structure of a subgroup. So where he proves the following: if you have 3 elements, so actually we can prove without the result using just Thomson results. And it says if you take 3 elements with product 1 and such that they are non-trivial and have coprime order, so the orders of the elements are coprime, then the group is non-solvable. So, and in fact, in order to prove the other direction, we actually need only that, but we use the result of Kaplan and Levy because they have a precise formulation, what we needed. Now I have a few minutes to talk about the groups where alpha characteristic of any irreducible is 1. So we know that if any non-trivial irreducible has characteristic bigger than 1, the group is solvable. What about the anti-solvable case? So, well, the anti-solvable groups, let's call group anti-solvable if every irreducible representation has trivial alpha characteristic. So let's denote this class by T by a Gothic T. Now, it's non-empty set, it contains the Yanko group. Now, we can show that if the group is in this class and its quotient and its normal subgroup are also in the same class. And we also know, I can show that the product of two groups from the class also belongs to that class. So therefore, the composition factors of T groups are non-abelian simple T groups. Now, we made some calculations in GAP, and among sporadic simple groups that you see here, only two of them, Yanka 1 and Yanka 3, belongs to that class, the others don't. So no alternating or no classical simple group of Lie type belongs to class T. So we have a conjecture, which I'm sure people who really knows representation theory could prove it very easily, so that all anti-solvable simple groups are sporadic. Now here I want to stop. Thank you for your patience.
Thank you, Misha, for this very good talk with very tricky proof. And are there any questions, comments, suggestions?
Can I ask a question?
Yeah.
Yes.
Sorry. Am I correct that the class of anti-solvable groups is not closed under taken subgroups?
It's not.
Okay. So it's not a complete class.
No, no, no. Only normal subgroups.
Normal subgroups and quotients.
Yes. And
Okay.
the products. Yeah.
Okay, thank you.
And really, we don't know. So I'm pretty sure that all anti-solvable simple groups should be sporadic, and one has to just run GAP program to check which of 26 sporadics belongs to that class.
Misha,
Yes.
you said that you are pretty sure that all non-sporadic simple groups cannot be anti-solvable. Do you have
Yes.
something under this? I mean,
Yes, yes, I can tell you why. Because if you take simple group of Lie type,
yep,
then they have so-called cuspidal representations.
yep,
And as far as I understand that, the alpha characteristic of cuspidal representation is divisible by P, where P is the characteristic of the group. So if what I said now is true, then all this group you can remove from the list. For alternating group, there is always an irreducible representation where alpha characteristic is 2. And I think Eugenia Gianelli somewhere told about that, but I didn't find the written text where it's formulated. Okay, so
Thank
that's
I see.